All right, so we're going to take a look at 12.4. So we're going to take a look at a different type of limit now. So the limits we've been investigating so far have been at a finite value. So x approaches 7, x approaches -1. Now we're going to look at limits at infinity. So and being able to do limits of sequences as well. That's kind of our part 2. So for today, our big essential question is, how can I evaluate limits of functions at infinity? So the limit of a function f of x as x approaches infinity or negative infinity. Now, thankfully, we've already really had this conversation earlier in the year when we looked at horizontal asymptotes and end behavior. Looking at what the end behavior of your graph is exactly the same thing as doing an infinite limit. So the awesome thing about this is you've already done everything that you need to. We're just going to put the symbolism to it to make that a little bit more clear. So here's what we're going to do. We're going to start with the review question. We would have done this earlier in the year. We talked about rational functions. So can you go ahead and let's think about the domain of this function first. So set that denominator equal to 0. So the domain would be all real numbers, but x could not be equal to 0. So the question is, at 0, what's going to be happening in the graph? Is that a removable discontinuity or not? So you can go ahead and graph it to take a peek. We're going to go back and have these conversations though that we did before. I don't think we can factor out an x, right? So I'm thinking we're going to be seeing a vertical asymptote at that location. So there should be a vertical asymptote when you go ahead and make your graph here. Looks like there's going to be a vertical asymptote on our graph at x equals 0. So you can go ahead and graph it on your graphing calculator. I just wanted to have one that I can write all over here. So we have a vertical asymptote at x equals 0. So we can't remove that discontinuity. It's an infinite one. So what about horizontal asymptote? So we would look at end behavior. So one way we talked about end behavior earlier in the year is we just graphed it and we trace along the graph to see what happened. If it flattens out and it looks like it approaches the same thing from both ends, we would have a horizontal asymptote. So we talked about this idea of end behavior. So the value of the function f of x approaches or y approaches, you can say either one, looks like it's approaching a half as x approaches positive infinity. Remember our end behavior sentences here? And f of x also approaches a half as x approaches negative infinity. So both ends of the graph looks like it's leveling out at a half on both of those. So if you look into your graphing calculator, look in your table, pick really big values, we can see that that's what's happening. So sometimes it's easier to actually like go out now in your table here, and you can trace and see as we get bigger and bigger values. So as x approaches infinity, it looks like it's getting closer and closer to 0.5, and you can do the same in the other direction. So it's kind of nice to have that validation. So looks like then we would say then, oh yeah, there's a horizontal asymptote at y equals a half. So being able to say there's a horizontal asymptote is the same thing as being able to talk about a limit. So being able to look at a limit. So in this case, we would say the limit. So we're going to talk about that same language we did before. Now, as x approaches infinity, so we looked at the going into the right of this function was a half. So that's kind of this first sentence, being able to do that. And then the second sentence would be the limit as x approaches negative infinity of f of x is also 1/2. That would be coming from this second sentence. So we can say the same things we did before, but now f is approaching, or x is approaching either infinity or negative infinity. Some people might ask, can we combine these two into a single sentence? We absolutely can. Some people would say the limit as x approaches plus or minus infinity is equal to the same on both ends. That's why we have a horizontal asymptote. So it's equal to a half. I'm curious if anybody remembers the shortcut way of figuring out that horizontal asymptote, figuring out that end behavior. Remember we had a big conversation about the degrees of these polynomials. So if you had a ratio of a rational function, a ratio of polynomials, the degree on the top is 1. The degree on the bottom also 1. If the degrees are equal, remember it goes to the ratio of the leading coefficients, so 1/2. So hopefully you can remember, we'll go back to that table again and fill out those values, but that's going to be doing the same thing. So looking for a limit is the same as looking for end behavior, and you've already done that, which makes this conversation hopefully a little bit easier. All right, so let's talk about defining limits at infinity then, how we write them. So we already kind of talked about that for our warm-up example. So the limit as x approaches negative infinity of a function, we'll say call that not Li, L1. So whatever it is at that end. And the two ends could be the same, but they don't have to be. The limit as x approaches positive infinity of a function, we'll call that L2. So we can say then f of x approaches L1 as x approaches negative infinity. So here's your kind of your or. And then we can say f of x approaches L2 as x approaches positive infinity. So this is kind of the or, the other end of the sentence. So it's the same two sentences we wrote when we talked about end behavior. So that's how we define limits. Now, we did a lot of things earlier in the year to talk about how to calculate these, and earlier in chapter 7 or chapter 12. One thing that's going to help us is knowing what happens to a ratio to be able to see what's happening at the ends of the graph. And so for both of these, it goes back to the properties of limits from 12.1. If you have anything 1 over x raised to any power, so any positive real numbers like 1 over x, 1 over x squared, 1 over x cubed, any of those kinds of ratios, what ends up happening as x gets really, really big, the bottom's going to get huge and the top is going to stay 1. So that limit, that end behavior is always going to go to 0. And it doesn't matter if it's positive or negative x values, it's still going to go to 0. The bottom number is going to get very, very large. So when you're taking a look at trying to find a limit, we're always sort of comparing back to what these ratios are doing. What's growing faster? Is it faster growth in the top, or is it faster growth in the bottom? Being able to look at those. So we're going to take a look at several of these and talk about what we can do to calculate those limits. So let's take a look at what would happen. The limit as x approaches infinity of 2 over x squared. So I'm going to have you go ahead and graph it. All right, so our 2 over x squared kind of looks like the volcano graph again. What we're trying to see is the limit as x approaches infinity. I know a lot of people are going to think about, well, it doesn't have a limit at 0. No, you're right. But we're looking at the ends of the graph now, so positive infinity. So we're thinking about that end of the graph. So when we think about this picture, so we have our undefined place at 0. What we're thinking about, if we're talking about x approaches positive infinity, we're meaning as the x gets bigger and bigger and bigger, so going in that direction, what are the y values doing? What are they getting closer and closer to? From the graph, sure looks like it's approaching 0. And if you look at your table, kind of a great way to kind of reinforce that for yourself, if you look at the table, the bigger and bigger values of x you pick, sure looks like those values getting smaller. Notice we're already into scientific notation there, so really close to 0. So I'm guessing that my limit for this is going to be 0. How can I know that? Where's the degree larger? So I want you to think back to all the things we talked about before. So the degree in the numerator is actually 0. The degree in the denominator is 2. So when we are talking about horizontal asymptote or end behavior, if the degree is greater, so the degree is greater in the denominator, that means this is going to go to 0 every time. So if the degree is bigger in the denominator, the ratio goes to 0. So the ratio is going to approach 0. So we can tell it by the graph. We know that that's happening, but it's growing faster in the denominator. What that means is that 1 over x squared is going to 0. Doesn't really matter if you have a 2 in the top or not. The 2 is not going to grow. It's a constant. The x squared is going to get bigger and bigger and bigger. So the denominator gets larger. The ratio goes to 0. So if you remember the degree bigger on the bottom, ratio goes to 0. All right, let's take a look at the next one. So we're going to try to see if we can figure out what this limit would look like. So we can look at the graph. We're hoping to take a look though and see what happens to each of these ratios as x gets really, really big. So kind of an algebraic approach if it helps you to sort of see what's happening. We didn't have a lot going on in that last one. We could have done it this way as well. Some people like to take a more algebraic approach. We only had a single term though. There's not really much else to do in that one. What if we write each of these as a ratio as well? So we can look at what each ratio does. So I'd have 1 over the x cubed. You'd have a 5x over the x cubed. And then you'd have a 3x cubed over an x cubed. And what we'd want to do is take a look at what each of these ratios do as x gets really, really big. Let's see if we can simplify them first. So 1 over x cubed you can't do anything with. We'd have 5 over x squared, and then we'd have a 3. All right, so when we're evaluating a limit, what we're looking at is what happens to each of these pieces. So what happens to 1 over x cubed as x gets really, really big? Well, it goes to 0 because the denominator is going to grow. What happens to 5 over x squared? The same exact thing. So it's going to go to 0 as well. Here's the interesting one. What happens to a negative 3 as x gets really, really big? Absolutely nothing. There's no x with it. It can't change. So it's a constant. It's going to stay at negative 3, and we can put our values together. So 0 plus 0 plus negative 3 sure looks like the limit then for this should be negative 3. So let's take a look at the graph first and see if that makes sense from the picture. All right, so I have my equation in there. Let's take a look at the graph. So we're looking at as x gets big. So we're looking at the end of the graph here. Well, it sure looks like as we're going along there, the more we go to the right, it's flattening out at -3. And again, if you go to your table, take a look. The bigger and bigger values of x, we're getting down closer and closer and closer and closer to -3. For those of you with a lot of time on your hands, you could figure out, hey, when does it change over to -3? I don't have that much time. Oh, I do have that much time. Awesome. 101. There we go. -3. Why is the calculator doing that? It's running out of decimal places, right? So we know it's going to approach, not equal at the end there, but we definitely are having that as our limit. So we can see it from the picture. Now let's see the shortcut if we can go back. Hopefully you remember, let's check our degrees. What's the degree in the top? Degree is 3, degree in the bottom, also 3, so they're equal. If the degrees are equal, remember it goes to the leading coefficients. Now just be careful, that's the highest degree coefficient, so it'd be -3/1, which is -3. So it's the same exact rules we did. If you look back in your, find your horizontal asymptote rules, it's literally the same thing. All right, so let's try a couple and see if we can figure out what those values are. So I'm going to scooch this up here so we don't need that on the bottom there. Let's try these three and see if we can figure out what we think the limit would be as x approaches infinity for each one. So let's start with the first one, letter A. We want to see if we can figure out the limit as x approaches infinity for 2x over 1 minus x squared. So I'm writing it as a as a limit sentence. So as x gets bigger and bigger, what's going to happen to this scenario? So we could graph it first so you can take a peek and see what that looks like. It's always a nice idea to see what the picture looks like. So let's do that. All right, so take a peek at your graph here. We're looking at the end behavior again. So we want the ends of the graph. So don't worry about those vertical asymptotes. There's definitely places where we're going to have undefined places, but we're talking about the end as x gets big. Sure looks like it's going towards the x-axis there down at the right end. So we're looking at this end, oops, that end of the graph. Sorry, I got rid of my picture there. So if I go to my table and I'm looking at the end, it's coming up from underneath, but as I pick bigger and bigger values, this looks like it's getting closer and closer and closer to, looks like 0. So if I had to guess a limit, I would say 0. Let's go to our shortcut. What's the degree in the top? So the degree is 1. What's the degree in the bottom? 2. So it looks like when the degree is greater, so the degree is greater in the denominator, that means this is going to go to 0 because it's growing faster in the bottom. So every time you see a degree greater in the bottom, I know that's going to have a 0 limit, also would have a 0 horizontal asymptote, right? It's the same conversation and behavior. All right, let's take a look at the next one. 2x over 1 minus x. Let's go ahead and take a peek at that graph, and we want to see what would the limit be as x approaches infinity of 2x over 1 minus x. Now, if you notice, the only difference in these two equations is that x to the first power in the denominator. All right, so I changed that to just an x. Now watch what happens in the graph. So my end behavior of the graph, again, I'm looking at the right end. What does it look like that's flattening out at? Looks like it's -2. If I go to my table and double check, well, sure enough, as I get bigger and bigger values, sure looks like it's getting closer and closer to -2. So I'm guessing that this limit is -2. What's the shortcut though? Is there a faster way without graphing it? Well, the degree in the top is 1. Oops, the degree in the bottom also 1. So it should go to the coefficients of those highest degree terms. That's 2 on the top. Careful, that's -1 on the bottom. So 2 over -1, there's your -2. So looking for that relationship, the same thing we did with horizontal asymptotes, really handy. All right, let's take a look at the last one and see if we can come up with our kind of our shortcut here. So the limit as x approaches infinity of 2x squared over 1 minus x. All right, so notice the change that I made in this one from the last one is I am now squaring the x in the numerator. All right, so I have my new equation. I squared that x in the numerator. Let's take a look at the graph. Wow. Okay, what's happening at the end of the graph? Well, we can't really see a bunch. There's this little piece down at the bottom. I'm going to make my window here my y min because we want to see as x gets big, and that's kind of going off the end. What if I made it -100 even? So, okay, now I can see it looks like it's kind of tailing off as the x's get bigger. So if you're looking at the right end of the graph, it's going down. If I look at my table, if I look at what the y values are doing, they're getting smaller and smaller. They're, growing, I guess, infinitely in the negative direction, if you want to think about that. They're not approaching a particular number. See how they just keep getting larger in the negative direction? The limit doesn't exist. It's not approaching a single value. This does not exist. I'm curious if you can tell from the original equation why that is. What's the degree in the top? So the degree is 2. The degree in the bottom is only 1. The degree is greater in the numerator. All right, well, what does that tell you? It's growing faster in the top than it is in the bottom. The limit's never going to exist. It's going to keep growing and growing and growing and growing. So the degree is greater in the numerator. That means the limit does not exist. So DNE. So we have these same things. It's the same thing with when we did horizontal asymptotes. Remember, if the degree is bigger in the top than it is in the bottom, it didn't have a horizontal asymptote. Now, in this case, I'm curious if you remember, it's a degree 2 over a degree 1. Take a look back at your graph. What kind, I'm going to go back to my regular window here, what kind of asymptote did it actually have? Well, it was a slant. You can see how it's slanted like that. So it doesn't definitely have a horizontal, so there's no limit. This one would have a slant asymptote. If the degree is bigger by exactly 1, that's when that happens. If the degree was bigger in the top by even more, still doesn't have a limit, still doesn't have a horizontal asymptote. It never can. So let's see if we can pull this together. So look at the graph and the end behavior. Let's see if we can fill this out. So we know that the same things are going to happen for horizontal asymptotes as limits. So it's a nice kind of refresher going back. So if the degree in the numerator is less, so that means the degree on the top is smaller than the degree on the bottom. In other words, the bottom is growing faster. The limit is always going to be 0. That's like the first example we just did. If the degrees are equal, so the degrees are equal, the limit does exist. So the limit exists, and it's the ratio of the leading coefficients. Remember, that means the coefficients of the highest degree terms. So don't get caught if they're not listed first. You got to hunt for them, make sure. So the ratio of the leading coefficients. So it exists when the degree is greater on the bottom. It exists if the degrees are equal. If the degree of the numerator is bigger, the limit does not exist. DNE. This is the situation where it's never going to work. So we have to take a look at that and see what's happening for those values. So remember that not every rational function has the horizontal asymptote. That's that last situation. But if it does, that value is always going to be the limit as x approaches infinity or negative infinity. So it's kind of a nice tool to help you remember what's going to be happening with those. So always look at the values of your degree, top and bottom. So we're looking at infinite limits. We can definitely use the graph to help us, and we're looking at that same conversation as end behavior.